And then as far as the material breakdown, let me again mention what to expect. What you should expect is to study for the last set of material, that's homeworks 10, 11, and 12. Study for those, know that stuff well. Study for that as if it's a midterm. So that means expect that stuff to be emphasized. One long answer question will be on that material, or so basically 50%. One of the long answer questions will be on something from exam 1 or 2. They may appear as just one old, one new, or they may be mixed together, but it'll be about 50%, 50% of each. For the multiple choice questions, again, it's cumulative, but emphasizing the last set of material. You're going to have to read the tea leaves, whatever you think that means. I'm not going to commit to a number of questions on old versus new. There'll be more of the multiple choice questions than on a midterm, but certainly not that many more. So think of this as a little bit of a supersized midterm that you get a much longer time to do. And so the key for this exam is make sure to know this stuff well, but maybe not go for speed as much as making sure that you know the broad cross-section of the material fairly well. For the old stuff, start with the midterms, okay? That should give you a strong clue as to what I emphasize, what I think is important. I'm not going to be pulling out some weird stuff from the old stuff on the final. It's going to be main important things, things I'll talk about today, main important things to get from the earlier stuff. And hopefully that's still reasonably kind of in the back of your head that you just need a little refreshment on, and then you can focus on studying for the new material as well. Okay, are there any questions on format before I launch into it? Okay, so I'm going to present this in a little bit more of a holistic way. What I'm going to do is I'm going to kind of try to make groupings and connections that you may not have kind of seen the forest for the trees as we went. So let me first talk about kinematics. So kinematics is the description of motion. And we ended up really having 5 variables that we focused on. The displacement, velocity, initial and final, acceleration, and time. And if you were lucky enough, the acceleration was constant, and that was about the most complicated motion that we took a serious look at when we were doing kinematics. So usually this was constant. In fact, if you're using the constant acceleration equations, they have to be constant. Of course, in kinematics, we get up to 2-dimensional stuff. So, for instance, for projectile motion, be very careful to split off into 2 streams, right? So don't plug in an x variable for a y thing or vice versa. It's really important to keep them straight. For projectile motion, the acceleration we usually used, well, there was no acceleration at all in the x direction. And so make sure you just cut to the chase, okay? You don't need to have doing all those equations or anything for the x direction. Just use distance equals rate times time. It was the y direction where it necessitated some doing. We usually picked up to be positive. In this case, this was minus 9.8 meters per second squared. That was the acceleration we found when you weren't going too high above the Earth. And then, of course, you have your 5 equations. Okay? And which of the 5 equations you use, remember that's judged off of which variable is don't know, don't care. So, for instance, if you have, you know, this and this and this, well, I guess that would be, this already counts as a known. So, if you want to know these 3 things, you want to find the time, and you don't know, don't care about the displacement. That's what tells you which equation to use. So, in this case, for example, would be equation number 1, because equation number 1 is missing displacement entirely. So, that was the beginning part of the course, and when we got into two-dimensional projectile motion, that was about the most complicated thing we did with kinematics. Yes, there were other kinematics variables. We talked about average velocity, we talked about distance, but these are the big, important, big hits, okay? And then, I guess we also graphed them versus time, so we did make some plots versus time. That's the essence of your kinematics unit. When we later talked about angular kinematics, it's the same deal. We have our 5 variables. They look different. But same exact idea. So this requires that there be constant angular acceleration in order for you to use those equations. And that just simply means that you're speeding up and slowing down smoothly along a circle. So that's the most complicated thing you can do, is you can speed up or slow down going along a circle, but not in some kind of weird herky-jerky way, smoothly. And same idea, you have 1, 2, 3 variables, you're looking for a 4th. Don't know, don't care about the 5th, and that tells you which equation to use. In this case, equation number 1. And here, you don't even have to worry about there being a second dimension. We did not do anything like that in this class. This is two-dimensional motion, but remember, angular kinematics allows us to still handle it in one dimension, because we basically wrap our one dimension around a circle. If you go counterclockwise, that's plus. If it's clockwise, it's minus. So we can use all the same ideas we did on a single axis, only now it's going in a circle. Now, of course, what we pay for that, by pretending that this is along a single axis when it's really in a circle, if you want to connect the angular to the linear, there's convergence, right? So, for instance, if you want to find out the distance you actually traveled, you have to multiply the delta theta by r. If you want to know the actual speed in meters per second, you have to multiply your angular speed by the radius that you're doing it at, and likewise, alpha tells you about how you're changing your speed. If you multiply by that by r, you'll get a tan, which is the equivalent, which tells you how much your velocity is changing in meters per second squared. And then, of course, you have to remember the unsung hero, centripetal acceleration. So centripetal acceleration, there is no analog in angular kinematics, because angular kinematics automatically already assumes you're going in a circle. Whereas we have to remember, you can't go in a circle for free. So you need a force and acceleration to hold you there in order to actually go in a circle. Occasionally, we might acknowledge that these two accelerations are really components of one whole acceleration. So you can think of the acceleration as what changes the velocity, but in order to make it more digestible, you can think of it as acentripetal, make sure that your velocity stays in turning, whereas atan is what changes the size of your velocity. You can go faster or slower. So that's basically your kinematics, where we just describe the motion in either linear fashion or in the angular side. Are there any questions on that before I move forward? Okay, so the next layer of the onion was, where does this stuff come from? Okay, you don't accelerate just because you feel like it. So we learned that you can't accelerate unless you have a force. You can't angularly accelerate unless you have a torque. So there are causes for these things. In fact, Newton's first law tells us that you can't accelerate unless there's a force. In fact, Newton's first law tells us there's a thing called inertia, where if you leave an object alone, it does exactly what it does all the time without any change. So that's what brings us to the next layer. F net equals ma. And it's equivalent in the rotational world. So, later on we learned in F net equals ma, the a is really the acceleration of the center of mass only. That was of no concern to us in the beginning part of the course because all our objects, whether we acknowledge it or not, were simply point particles. They didn't have any size or shape. They didn't have different parts that could move differently. But if you have some object that does have some size or shape, and you exert a net force on it, it's really only the center of mass that will have to obey this law. For the rest of the points, this is the law that applies. So this force also has leverage around this pivot. It will also cause a torque. So how do you compute torque? This is the equation. And it has several more ingredients than just the force, although that is one of them. It's important that you address the leverage that the force has, and also the force orientation. Those are things that are going to determine whether this force is useful for rotation or not. So, for instance, if you're opening a door, it matters that you're pushing away from the hinge. It matters that you're not pushing in the wrong direction. For us, most of the time, theta was equal to either 0 or 90, which means that this is equal to 0 or 1. So the force is actually completely useless or completely useful for rotation. So once you have to make that decision, that's the only decision you really have to make in my class. Okay? So the sine of theta that is there to kind of remind you what's going on, but where most of the time it's going to be 0 or 1. For the plus and minus, same deal. This is counterclockwise. This is clockwise. All the rotational quantities share that. And in this case, for instance, the torque, we might say it is minus because it is clockwise. Okay? So you can see that that force is going to exert a torque. It has leverage against the pivot. It's not pointed totally wrong. It's pointed somewhat. In fact, let me draw it so it's applied right here. Then you can see that that is applied at 90 degrees, and it's going to be most useful for torque. And you take R is this distance right here. That's how far it's applied from the pivot. So that would cause a torque that's negative or clockwise, and of course the angular acceleration is the same way. So let's look at the connective tissue here. How much force, how much acceleration are you going to get for your force? Just need to put in the mass. The mass is what measured how stubborn it is to acceleration. This gets a little bit more complicated. The rotational inertia, you have to consider mass, mass distribution, and axis of rotation. So this is where you have two options. If it's a collection of point particles, you just add up all the contributions. But as I saw when I was grading the second exam, it has to be a collection of point particles. If you have an extended object, you have to use the formula. So I equals, look at the table. So if it's a solid panel, use the rotational inertia of a solid panel, not a point mass. Okay? So there's a whole table available for you on the second page of the equation sheet. You should be able to go there and find whatever extended object I've given you. Okay? So don't just use mr squared all the time. All right? So this tells us, of course, what acceleration could I put into my kinematics equations? What angular acceleration could I put into my angular kinematics, right? So this is where we get the accelerations. If we're not handed them on a silver platter, this is where we get the accelerations to put into that, right? Now remember, these have to be constant to be able to use them in the constant angular acceleration and regular acceleration equations. So constant A and alpha is important, which means that these have to be constant too. that may not always be the case. So if you have some kind of more complicated motion, you're going to have to use some other technique. Probably most likely energy. Okay? Energy is the big technique we had for doing complicated motions because energy does not rely on acceleration being constant. So that's a dead giveaway. If you're faced on the final exam with choosing a method, if you look at that situation and go, those forces are evolving with time. They're not constant. Use energy. That's a dead giveaway. On the other direction, the dead giveaway is if you get asked for time, then energy, that's the one downfall of the energy method, right? You can't do time. So if you get asked for time, then you know to use this stuff, okay? Now, if you have a situation where you think the forces aren't constant and you're asked for time, either you're mistaken or there's a problem with the question, because I would never ask you that, okay? Anytime I would ask you for the time, the only way you have to get that is the kinematics equations, and those rely on constant acceleration. I think the one exception is in simple harmonic motion, where I had to just hand you from on high the period formula, because that is a situation where I want you to be able to address the time it takes for something to oscillate, but the acceleration is definitely not constant. Okay? But other than that, there's one fork in the road that you can make some decisions. If you get asked for time and it's not a pendulum or a mass on a spring, okay, if you get asked for the time it takes to do something, it's an old stuff, kinematic stuff, exam 1. And if you get asked for some very complicated motion where the acceleration is not constant, it's going to be energy, exam 2. Okay, question?
What about when you have an extended object with another extended object on the end? So like a thin rod with a sphere on the end.
A thin rod with a sphere like this?
Yes.
Well, I did not give you the equation for a solid sphere around this axis. It was a point mass on the exam. Is that what you're thinking of?
I am. I'm thinking.
Okay, that wasn't a sphere. It was a point mass.
Oh, okay, okay.
So you can just combine, right? So if you look on the equation sheet, it'll tell you that if this has a mass m and a length L, and it's rotated around the pivot like this, the rotational inertia is 1/2 ml squared. If you now have a point mass m on this end, then you can add in the formula for that.
Okay, got it.
So you can just construct your rotational inertia out of different pieces. The important is to make sure that if this is a bar, you can't just assume it's a point mass. You have to use the bar formula.
Okay.
Are there any other questions? Okay, so I've already jumped the gun a little bit and mentioned energy here, but let me go back and do a survey of forces, right? Forces, there's a lot of things that could go into the net force. Remember what this is. This was a vector equation, so it got a little bit annoying to do. In fact, what I recommend is that you do it on 2 tracks, right? You do the X track and the Y track. This is a major theme in homeworks 4, 5, 6, and such. And to get the net force in the X direction, you have to add up all the X components. And similarly in the Y direction. So this required a comfort level with subdividing vectors into components. That's where your SOHCAHTOA comes in. Okay. So what I want to do is, rather than focusing on the math of it, vector addition, I want to show you the various ingredients that could come out. Right? So various ingredients, rather, that could go in. Let me do a survey of forces. The name of the force and our rule of thumb for its size and for its direction. I guess I'll leave a column for comments. We introduced a lot of these up front, obviously when we wanted to have forces to play around with in the homeworks 4, 5, 6. But we did occasionally introduce one even later on, so we should maybe let's take a survey. Force of gravity. That was the first one we introduced. Another name for it is weight. Okay. So weight is not the same thing as mass, okay? Our first dabble into it was that it was of size mg, because it was the magic force that always gave the same acceleration to everybody. Its direction was downward. And we used it even in situations where there were other forces acting that prevented the acceleration from actually being g. But that was the only thing we had to go off of, right? This idea that it's the force that gives the magic acceleration, 9.8 meters per second squared to everyone, okay? But now we can also go back and remember that we did eventually get down to the bottom of this and figure out what was going on with gravitation in the universal sense. So it turned out that two objects attracted each other simply because they had mass. And the way you figure that out is to multiply the two masses together and then divide by their center-to-center distance. Then multiply by this universal gravitational constant. And of course, this part, for objects near the Earth, turned out to be this. So if you take the universal gravitational constant, capital G, multiply by the Earth's mass and divide by the Earth's radius squared, you get 9.8 meters per second squared. And of course, the reason why it acts downward is simply because it's an attractive law. So objects on the Earth gets pulled down and the Earth gets pulled up in turn. So which one of these do you use? Well, you use this if the changes in height are relatively minimal. So if I throw a marker up in the air, yes, it's higher at the top of the flight than it is in my hand. Is it true that the force of gravity is slightly weaker on it when it's higher above the Earth? Sure, but minimally, right? So it doesn't matter. So I am safe in saying that the force of gravity on this pen is about the same here versus here. This is when you start to have major changes in the height, and therefore the force of gravity is not the same at the top and the bottom of the flight. So we're talking there about satellites and things like that, basically no longer everyday situations, right? So you can still safely use the stuff we did at the beginning of the class, as long as you have a baseball flying through the air or something where the height is not changing very much. And when I say changing minimally, of course, I mean compared to the radius of the whole Earth, which is 6 million meters. So no matter how good of an arm you have, you're not going to throw a baseball, an appreciable fraction of that into the air, right? We, of course, also found great use for this when we wanted to find out what is the local g somewhere else, right? So we found out, for instance, what would be at the g be at the surface of the moon, right? It's not the same thing. I had to do it for a planet X on the homework, right? So what's the acceleration due to gravity at some other location? I gave you enough data about the mass of that planet and its radius for you to be able to plug in and figure out what it is there. So there's a little bit about the force of gravity. We did that one in a kind of a 1-2 punch. First, basically, just some preliminary thing without really knowing what we were doing. The only way we got away with using this mg was because you guys did an experiment to show that the acceleration was roughly constant, and you got the value, 9.8 meters per second squared, even if at that time we had no idea why it was that yet. Then, homework 6, we finally peeled back the reality of this layer of onion here, what was going on with gravity. Other forces, we did the tension. I guess I should label what we call these: force of gravity, tension. The size varies depending on the situation. You kind of have to look for context. The tension can vary as needed, anywhere from 0 up to the maximum breaking strength of the string. The direction, it always pulls along the rope. So that rule of thumb was important, and probably the biggest thing we did with these pulley problems. So pulley problems was a chance for me to see if you really knew what you were doing with forces, because it's kind of like a 2-in-1. You set up the forces for one object, you set up the forces for another, and the way that they talk to each other is the fact that if they're connected by the same rope, the tension's the same, right? So we had one of these things here. You can say the tension's like this and the tension's like this, and you're making sure the tension always pulls, never pushes. So make sure it's the tail of the arrow that's pulling on the object. You should never have the tension pointed towards an object. Okay? So for pulley problems, we said that the tensions are the same and the accelerations are the same size, right? So that was kind of our way of solving those 2-in-1 problems. Did several of those on homework 5. Next force, normal force. This is the force from a solid surface. So don't include one if your object isn't touching a solid surface, okay? Again, the normal force varies. It varies with a purpose. It makes sure that the object's structural integrity is, or the surface's structural integrity is never violated. So no motion into the surface. That was the point of that. In fact, it's perpendicularly away from the surface. Now this is where I see a lot of students who haven't fully absorbed this concept. I see a lot of students writing n equals mg like it's a knee-jerk reaction. There are many situations where that's not true. So let me mention a couple of those right off. One example is when you're on an incline. The amount of force necessary to keep the object from getting smushed is the amount of force that's into the surface, which is mg cos theta. Remember, not all of the force of gravity is trying to violate the surface in that case. There's another component which is perfectly happy to pull the object parallel to the surface, and normal force doesn't have a problem with that one. So there, n is equal to mg cos theta, right? So you might say, okay, when it's a flat surface, I'm safe in saying n is equal to mg. Well, it depends. Let's say you're going over a bump. If you're going over a bump, you are not going straight, you're actually going on a turn. And if you're going on a turn, you need a centripetal force toward the middle, which in this case is downward. Now remember, centripetal force is not a new force. It's a condition that you must meet. So if you need a downward force in this case, then the force of gravity is going to have to be not the same size as the normal force. Okay? So in this case, the way you might set it up is the actual force meets the requirement. Let's say upward is positive. You have n up, you have mg down. Those are the two actual real-world forces that you have. Normal force is upward, away from the center. Gravity is downward toward the center, and you're going to have that one wins because your condition, if you want to go in a circle, is you need mv squared over r towards the center. So in this case, the force that's away, the wrong way, away from the center, is going to have to be smaller than the force toward the center if you want to have an overall force toward the center. So again, many situations in which n is not equal to mg. Generally, if I see that just written out on a problem where I ask you for the normal force and it's widely different, I usually just give 0 points because that's not at all helpful if you were to write n equals mg to everything. Okay? So n does not equal mg always. I see a lot of students that they never get past just writing n equals mg. Okay? So there's the normal force. I guess the other force in the beginning batch was the force of friction. So the force of friction, we actually noted that that was quite complicated. We have two kinds, static friction, which varies, and kinetic friction, which doesn't. I guess you could slide onto a different roughness surface, but if you don't do that. The way we talked about static friction was that it varied anywhere from 0 up to a maximum amount, depending on how hard you were trying to get it to go, trying to move it. And the maximum amount that it can hold back is determined by mu sub s times n, where mu sub s is the roughness coefficient of the surface, and n is the normal force, which is a measure of how hard the object and surface are pushed together. So this varies as needed. Don't forget the as needed part. There were several problems on homework number 5, which was meant to hammer home this idea that it's as needed. That's in contrast to kinetic friction, where you can just plug in chug. It's the kinetic coefficient times the normal force. Okay? And again, that n is normal force. It's not newtons. Okay? So it's not, make sure you plug in something for that. It's not just the units. Okay? So that's the frictional force. I guess the other thing I should mention, we talked about rolling a little bit later on in the course. For rolling, you can set this to 0. So when you're rolling, you are largely insulated, not perfectly, but for our purposes, you are largely insulated from the effects of friction. Okay, rolling is something where you get to move, but you also get to not rub against the surface. And therefore, you can safely set that to 0. Sometimes they call that rolling friction because it doesn't fit neatly into static or kinetic. So then what do we have? That did it for the first batch, but we did introduce several forces later on. Again, I'm not going to include centripetal force for a good reason. Remember, there's no special force in the world that only makes things go in circles. Okay, this does not belong on the list that I'm making. This is a condition that real-world forces do or do not meet. Okay, so real-world forces either can combine just right or fail at combining into the right amount, mv squared over r. And if they don't combine into that amount, that's fine. You just don't get to go in a circle. What else did we talk about? When we got to fluids, before we even did that, spring force. So spring force, the size of it is the spring constant times how far you take the spring from equilibrium. So K is basically the stiffness of the spring. Not all springs are identical. And then K times how far away you take it. All springs do not like to be away from their happy place. The more you stretch or compress it from the equilibrium, the more force it will exert. And in that direction, that force is towards the equilibrium, towards the spring equilibrium. Now, as far as including it in force calculations, we don't usually, because unless you are lucky enough for the displacement to be constant, which usually means the object is at rest, you will not get lucky enough for the spring force to be constant. And of course, constant is important if we're going to use the old forces method. If you have an object bouncing on the spring, the displacement constantly changes, the force constantly changes, the acceleration constantly changes, forget it. You're going to have to do that with energy. So I would say for the most part, we treat springs with energy. Okay, so those go into the energy method, and it was no accident that I waited so long to introduce springs because they play really nice with the energy method, but not so nice with the old stuff. So we have a formula for spring potential energy, and that's how we keep track of it. I'll get to that in just a moment. The final force I think that belongs on this list that we introduced, let me continue the same categories. That's the force from a pressure. So the force from a pressure, the size of it, you multiply the pressure that you have by the area which it's pushing on. That'll give you the force. And the direction of that is going to be towards, or I should say, the material causing the pressure wants to increase volume. So probably our most common use of this, we have some kind of area. We have a pressure pushing on one side, let's call that P1. That exerts some force. It wants to increase that pressure, whatever's causing it wants to increase its volume, so it wants to push that area out of the way. But it's in a competition, because there's another pressure from something else over here, and that wants to increase its volume, so it pushes back. So they both want to move that area out of the way so they can increase their volume. They can't both win, and so the net force ends up being the difference in that competition. And we find that the larger pressure always wins. So the net force will be in this direction. So remember, if you have a larger pressure and a smaller pressure, the larger pressure is going to win, the smaller pressure is going to have to take it. Okay? So the net force always points towards lower pressure. Now, one of the most important applications we have of that is if we have something that is either partially or totally submerged. So we learned that pressure increases with depth. And so what that means is that the water that's on the bottom part of this object is going to push harder than the air that's on top. So it's once again a competition between pressures. It's going to be a net upward force towards lower pressure. And in this case, we give it a name. We call it the buoyant force. So when the pressure difference is caused by the fact that the pressure increase is going into a fluid, we call it the buoyant force. And we found an extremely big shortcut for that. We found that the buoyant force is always equal to the weight of fluid you've displaced. So how much upward force do you get there? Exactly as much as this water weighs. And our reasoning for that is that water supports its own. So water would be held up if it were in that space. So if you replace that water with something else, the surrounding water does the same job. Okay? So the buoyant force is always equal to the weight of fluid displaced. That's always true. But that does not mean it's guaranteed to hold up the object, right? So this may be, the buoyant force may be greater, equal, or less than the weight of the object itself. And that will determine whether the object rises, stays in place, or sinks, right? So don't confuse those two weights. So that does it for the forces we've introduced. And if you're doing a force problem, that will necessitate one of both of these forces to be broken up into components. Use your force problem-solving strategy to make an intelligent decision about components, right? So which way are you going to put your x and y axes? What I recommend is that if you have an acceleration and you know which direction it is, put an axis in that direction. For instance, the inclined plane is a classic example. You want to set your x-axis to be either downhill or uphill, but along the incline, because you know that any acceleration is going to be there. You can't move perpendicular to the incline. Follow that force problem-solving strategy. I could, for instance, give you a new problem, including maybe some of these new forces, but the same strategy applies, right? You want to break them into components. Now, I've already talked about the fact that there is obviously limitations to the force method. If you want to find anything about the motion, the forces are going to have to be constant, the acceleration is going to have to be constant. So then that brings us to energy. Energy is really good if the acceleration is not constant. The one thing that it cannot address is time. Okay? So let me take a brief survey of what are things that are eligible here. E is mechanical energy. It comes in two general varieties. The energy that's in the motion and the energy that's stored and can't be seen. And we went ahead and we took, out of our forces, we took the gravity and the spring. Those are two conservative forces. And we made them into potential energies. So if we take our list of forces here, gravity is conservative, spring force is conservative. Of course, friction, that's definitely non-conservative, that goes in here, right? So we know that friction is complicated. It takes mechanical energy, sends it to heat, so it needs to be treated a little differently. How do you compute this? The old-fashioned way? The way you compute any work? We used to compute all works like this, from everything, before we made the distinction between conservative and non-conservative forces, right? Because we learned that conservative forces can instead be thought of as energies. So now, the way we work it is that it's really the work done by gravity that's sloshing back and forth these two forms of energy, right? We learned of work as a process of energy transfer. Positive work means it goes into kinetic energy, negative work means it goes out. But we do not see this explicitly, this is implicit, because of course we don't bother to compute the transaction if we keep track of the two accounts that it transfers back and forth between. So there's two forms of kinetic energy that we looked at. And if we just sum these guys, 1, 2, 3, 4, and we sum them later, if we get some exchanges, that's been done by conservative work. It's only when something doesn't get invited into the club, so this is heat, this is the work done by friction, because our mechanical energy club is restricted to these two types of energies. Anything that takes it out of that category completely is in our non-conservative work term. That's kind of our in and out valve to other things that we don't want to have to deal with. So that was an example of something that can take energy out of our mechanical entirely. What about these other guys? Well, tension and normal force, these can be also non-conservative. In fact, we talked about the fact that if you have an applied force, right, that's a place where energy can come in. So you can take chemical energy and send it in. So you can have a system that has more mechanical energy at the end than it did at the beginning. Classic example we did was lifting a crate, right? We lift a crate, its mechanical energy is increasing. So what are different ways for you to get chemical energy into a system? Well, you could pull on it with a rope, right? Or you could push on it with your hand, right? Those are all different ways. In fact, the one I erased here, of course, because it didn't make the bottom, that was the force from a pressure, right? The force from a pressure was another place where you can apply a force from some other means. And in fact, we worked that into Bernoulli's, right? When we did Bernoulli's, the non-conservative term from the pressure, when we arranged it around a little bit, we were able to still make it this conservation, except for it's this really weird conservation. It's not quite energy. It's a weird mix of quantities, right? For Bernoulli's, it's like kinetic energy, gravitational potential energy, and pressure, right? So it's this weird thing where we insist on trying to make it a conservation, even though the applied force went in this term, right? I should mention that it's possible for the tension and normal force to act at 90 degrees, in which case they do no work at all, right? So let me remind you that when a force is perpendicular to the motion, it does zero work at all. These things fall into guiding forces. It's not that the force itself is 0, but it never makes the thing go faster or slower. Classic example of that was work done by the normal force. Normal force very often was acting always 90 degrees to the motion, so it just guided the thing along. So your classic example of those roller coaster problems, if they're frictionless, the work done by the normal force is 0. The work done by friction is nothing because it's frictionless. And the work done by gravity is taken care of in the potential energy kinetic energy exchange. So you have just keep track of KE and PE. So that's kind of how energy works. I would certainly recommend that you take a look at some example problems that have these guys. I think the pinball example on homework 10 includes all 4. And because you're rolling, as we said, if you're rolling, you can neglect the frictional term, but you will need to consider anything that's rolling as having both forms of kinetic energy. One of the big shortcuts that we showed was for when you're rolling, your rotational kinetic energy is swiggle times your translational. That's a huge shortcut, and again, it's not on the equation sheet, so if you want to use it, you have to do the 2 lines of math that are required to get it. Okay. Now, what did I not touch upon? Momentum. So, momentum is another technique. When do you use it? When there's no net external force. Okay? So basically, a system is left alone. Look for something where it's a horizontal, frictionless surface or something like that. Make sure you can compare and contrast momentum conservation with energy conservation. One does not imply the other. That's where the inelastic collisions come in, right? And also, angular momentum conservation is the equivalent when the net external torque is 0. So look for some keywords like the Bob the Monkey problem, right? Frictionless pivot. So you know you're isolated from the outside world in terms of torques. Same deal, can you have energy coming in or going out from within? Yes, you can. So just because the angular momentum is conserved does not mean that energy is conserved. Okay? So those right there, that doesn't quite touch on everything. If you guys want me to talk about the remaining topics, I'll be happy to do that on Wednesday. Just gotta bring questions and tell me what you want me to talk about. Other than that, let's close it up for today.
Can I stop on that? Thank you.